So for this example, we have in 2015, the population of a small town was 8,000. The population is increasing at a rate of 2.5% per year. We're supposed to rewrite the exponential growth function to find the monthly growth rate. So this growth rate that they give us is a yearly growth rate. Now the way we're going to be doing this to find the monthly growth rate is we're first going to start off by writing the equation. So y equals ab to the power of x. And next, fill it in. So our starting amount is 8,000. So y equals 8,000 times, this is a growth function, so the actual growth factor will be 1 plus our growth rate, which is 2.5% as a decimal. 2.5% is divided by 100, or move the decimal place over 2 spaces, 0.025. So our growth factor is 1.025 to the power of x. Now we're going to be looking at the monthly growth rate next. Now to find that monthly growth rate, what we need to do is we need to make sure that x, or our variable representing our time, is multiplied by 12, but we can't just change it just because we need to. We have to balance it out. So we're going to use a trick that we did when we were rationalizing the denominator, when we multiply by the conjugate and stuff. And we're going to change our exponent to be 12 over 12 times x. 12 over 12 is actually 1, so we're not changing the value of the actual exponent itself, but it does change the format. So we're not actually changing the value of the expression, we are changing the format, however. Now that we have this, we can kind of separate it here. So y equals 8,000 times 1.025, and we're going to use the power of power property, which means we can separate this exponent as 1 over 12 times 12x. They're equivalent because of how you multiply fractions. And we're going to write it as 1 over 12 on the inside to the power of 12x. 12x would represent how many years, how many years go by, since there are 12 months in a year. And x now still representing the years. We're just now multiplying it by 12 to turn this into a monthly equation. We're still using x as years, but we are converting the growth factor into a monthly growth factor, and in turn turning it to a monthly growth rate. To finish doing that conversion, I just have to deal with this expression inside the parentheses. So we have 1.025 to the power of 1 over 12, which turns my equation into y equals 8,000 times 1.00206, I'll keep 3 of those decimal places there, to the power of 12x. So this would be the equation for that has it converted into a monthly growth factor. And to find the monthly growth rate, remember that this growth factor is 1.00206 is 1 minus the growth rate. Actually, no, 1 plus the growth rate, because this is growth, which means if I get r by itself, our growth rate, r, is 0.00206 or 0.206%, approximately, as the growth rate, monthly growth rate. In this example, we're investing $400 into an account that has an interest rate of 5%. We're going to be finding the amount in the account after 5 years if interest is compounded yearly and quarterly. So we're going to do it twice, once with a yearly compounding of the interest and once with the quarterly compounding. When we go to do this, the formula used for compound interest is A equals P times, in parentheses, 1 plus R over T, and then close the parentheses to the power of N times T. P is the principal or starting amount. A is the ending amount or amount after T years. N is the number of times per year it's compounded. R is the rate. And T is time in years. So if I go through and try to fill stuff in, we're looking for the amount if we compound the interest yearly. So our starting amount is 400. We have 1 plus the rate. Remember, you need to convert the rate into a decimal. Our interest rate is 5%. As a decimal, 5% is 0.05, either moving the decimal place over by 2 or dividing it by 100. So 0.05. We're compounding annually or yearly this time, which means that's 1 time per year. Yearly and annually are the same. And then to the power of 1 times our t, which is 5, because we're going for 5 years. Once I get it set up, I can just type it into a calculator or do it piece by piece, doesn't really matter. 400 times 1 plus 0.05. I don't really have to divide by this one, but I'm going to. Just save some trouble later, whenever I do the quarterly. And then in the exponent, I do need to put it in parentheses, 1 times 5. And again, I don't actually need to do that, but since I'm doing 2 different exponents here, I'm just going to easily switch it. So if I type this in, I'll get $510.51. There we have for part A. Now if we do the same thing for a quarterly, when it's compounded quarterly, well, quarterly just means it's compounded 4 times a year. There's 4 quarters in a year. So 1 plus 0.05, still most of the stuff is the same. However, n is going to be different. We're compounding now 4 times a year. So we have 4 times t, which is going to be still the 5. So if we go to my calculator and type this in, we are compounding 4 times, so the only number that's changing is my value for n. Now you can see that it is $512.81 approximately, as far as how much the investment is worth. So comparing the two, just quickly here, you can see that the more times it's compounded for quarterly, the better off profit, or the bigger profit you'll have on it. This is not a big difference right here. It's only a difference of $2, but that's because our initial investment is pretty small. If that initial investment was a lot bigger, so let's just show that real quick. If I duplicate this equation and I change one of them back to a 1, see if I can, there we go. So if I take a look at my initial investment, so right now we have both of them on there, and I add another 0 to my initial investment, that's still not that much, but now the difference is $20 rather than just $2. And as we add more zeros, as we add a larger starting amount, that difference becomes a lot bigger. Now the difference is $200. So the more times it's compounded, the more interest is earned. But it also is affected by how much you start with as well. That also helps to determine how much interest is actually earned on it. So at higher values, there's a more drastic difference between the number of times it's compounded. So in this example, we're investing a $400 investment into an account that has an interest rate of 5%. Find the amount in the account after 5 years if the interest is compounded continuously. So if it's continuously compounded, this is the formula that we use. It's slightly different from the normal compounded interest formula. The main difference is this base. This base is now E, which is the natural base. I believe it's actually called Euler's constant as well. But it's found from limiting process, which just expands upon what we had before if we add higher amounts of compounding per year. If that value for n for the normal compound interest formula keeps increasing. But with that, we're just going to go ahead and apply it. Like before, P is the principal, E is an actual number, kind of like pi, it's irrational. R is our interest rate, and T is time. So those are the things we usually have to fill out here. So we have our principal is $400. E is a number. Most calculators have an E button if it's a scientific calculator or above. Our interest rate is 5%, so as a decimal, that's 0.05. And we're investing for 5 years. So 0.05 times 5. If I go and try to type this stuff into the calculator, we have 400 times E to the power of, I'll put this in parentheses because there's two things in the exponent, 0.05 times 5. So we get $513.61. So this is the same situation as before, as the earlier example. It's just now we're compounding continuously, and you can see this has an even greater profit than the other ones. The more times it's compounded, the more interest is earned. So in this example, Willis knew that the number of followers he had on TikTok was growing exponentially. He started on TikTok in 2010 and recorded the data for each year. In 2022, he had 8,000 followers. In 2023, he had 9,600 followers. Write a model that can model his followers' future growth. So if we go through this, we don't have actually the starting information this time. From when he started in 2010. So what we're going to have to do is kind of work a little bit backwards. So we do know 2 years. We know 2022 and 2023. But he is starting in 2010. So if we set up the general equation for exponential growth, which again is y equals a times b to the power of x, we can kind of work ourselves backwards to find everything. So I'm going to set up two instances of this. The first one is for 2022. In 2022, he had 8,000 followers, which is the y value. We don't know how much he's starting with, and we don't know the growth factor. But we do know how many years have passed since it's 2022 and he started in 2010. 12 years have passed. And we can also set up one for 2023. So if 2023, 9,600 followers is equal to a times b to the power of, well, in 2023, 13 years would have passed. So we have both an x and y value. Now, remember that even though we don't know what a and b are, we do know that these sides are equivalent. They're equal to each other. So the 8,000 is equal to whatever a times b to the power of x to the 12 is. And for both equations, a and b are the same thing. So we can use a strategy here, very similar to systems of equations. Our strategy, and there are other approaches to this, our strategy will just be to divide the second equation by the first equation. What happens when we do this is, well, we will divide 9,600 divided by 8,000. I hate that the keyboard comes up every time I switch that. 9,600 divided by 8,000. Remember, we can do this because we do know that those are the same. We just don't know what those values are as of yet. So if I do this division, I get, trying to make it so I don't have to keep doing that. We get 1.2. On the right side, the a's cancel out. And when you divide variables, you can subtract their exponents. So 13 minus 12 is b to the first, or just b. So we easily found what b is. Now, if they are sequential, if the years are sequential, you can essentially just divide the later year by the first year and find the same thing. But approaching it this way works even if the years are not sequential. You would just have an extra step to get rid of the exponent if the years aren't sequential. But now that we have b, we can use the other formula and just go back and continue to work. So 8,000, again, it's essentially a system of equations. 8,000 times a times b, which is now we know is 1.2 to the power of 12. And we just have to solve for a. 1.2 to the power of 12, I don't think that's going to be a pretty number. 2 to the power of 12. Oops, it didn't register. I clicked the power thing. And not a pretty number. So I'm just going to go ahead and divide it as is. I will divide it as 1.2 to the power of 12 on both sides. They'll cancel out on the right side. And then I'll just type 8,000 divided by 1.2 to the power of 12, which will be a little bit nicer in the long run. Trying to get that. Yeah, it's not letting me. Not letting me change the size of that. Oh well. So my 8,000 divided by my 1.2, and it keeps not registering things because I have it so narrow here, to the power of 12, there we go, gives us that the starting amount is about 897.2. Since we're talking followers here, we'll just go 897. We'll round to the nearest whole value. So we have 897 as the initial starting amount. So overall, the equation to model the situation would be y equals 897. I think I keep saying 8,000. times 1.2 to the power of x to model the situation. The growth factor, just emphasizing some of our vocabulary word, the growth factor is 1.2, which means the growth rate, because remember the growth factor is 1 plus the rate, so the growth rate would be 0.2 or 20% as a percent. Just emphasizing some of the vocabulary. And that's it.